Hello everyone, today we are going to look at the last part of our energy chapter. Yay! So we look at the energy that you can store in a spring. Now, or elastic band, right? So a spring or elastic band. So now we can store energy in gravity. So for example, when you pick up something and before you drop it to the ground, it has energy. It's called potential energy, remember? Now, because if you release the object is going to hit the ground, it's going to do some damage. So those potential energy converts into kinetic energy, right? But we can also have energy uh, stored in batteries. That's how a lot of the appliances that we use, for example, your cell phone actually works. It uses the energy stored in a battery. So you can store energy in gravity, in height. You can store energy in batteries. There's another way to store energy, which is in a spring. So when you have a spring loaded, for example, a toy, when you load the spring, when you compress it, there's energy stored in that, right? So let's say this is the spring right now. I have a spring in here. So what happens is you can do two things to it. You can stretch it. So what happens when you stretch it? When you stretch it, it has a tendency to go back to its normal shape. So there's energy stored in there. Now, but what happens when you compress it? When you compress it, it also doesn't really want to be compressed, and it will also try to bounce back to a normal shape. So there are energy stored in compressing or stretching a spring. So we have this term called elastic potential energy because the energy is stored in something that is elastic, right? A spring, a bungee jump cord, a spring, or a rubber band, they're all elastic stuff. So they store energy. So elastic energy is the stored energy in an elastic object. So there are a lot of elastic objects. Even like a soccer ball is elastic object. Technically, anything bends a little bit, like plastic. You can bend plastic, like a ruler. You can bend it a little bit, right? So there are energy stored in that. Okay. So what are some elastic mediums? So for example, if you want to, spring would be an obvious choice because that's also so spring is the obvious choice. But you can also have elastic elastic band, rubber band if you want it, or bungee cord, or a lot of other things. Okay, so the amount of energy that you can store in it is governed by something called elastic force. Okay, so Hooke's law is a law that is developed by Hooke, which is a scientist back then. So we name after him to describe the amount of force we can store in a spring or a elastic band. Now that equation you already know. It's called the elastic force equation or the spring force equation, which is negative k times the change in the length of an object. So remember that one, right? So in this equation, the k value in here is the spring constant. Well, actually, you know what? We will wait until the energy equation to actually define those because they're exactly the same. So the negative sign above just indicate the fact that, the force is going to be opposite to what you apply to it. So for example, if you compress a spring, the spring has a force that's trying to go back to normal, so expand. If you stretch a spring, the spring has a force that try to go back to its normal shape, which is, in the other direction. So the force is always opposite to what you did to it. Now, so that's the force. How about the energy? So what if we want to know the amount of energy you can store in a spring? Now, so then we have a spring potential energy. Okay, so it's potential energy for spring. And that has the equation of 1/2 K delta X squared. So it's almost like the kinetic energy equation, which is 1/2 mv squared, right? So this one is 1/2 K delta X squared. So 1/2 K X squared. So now, in this case, now we can define those terms. So K is the spring constant. So if you remember from the fourth chapter, spring constant is a specific number that you're either given that number in the question or you're looking for it. And the spring constant is measured in Newton per meter, which is how many Newton of force are you going to get from the spring if you stretch it for 1 meter. So for example, if a spring has a spring constant of 1,000, that means if you stretch a spring for a meter longer than its usual length, then it will give you 1,000 Newton of force, right? So, okay, so what about X? X is the amount of, so X is the displacement, from its equilibrium position. So now a spring, when it's not stretched, it's just sitting there. It has a normal length, right? So we call that normal length is equilibrium position. So for example, I have a spring right now, and let's say this spring measures, so let's say this spring measure 5 meters, right? And that is its equilibrium position. Now, so what happened is I can take that spring and I can stretch it. So let's say after I stretch it, this spring now has a length that is longer. Oops. That's longer than 5 meters. So let's say now it has a length of 12 meters. So what is delta x? 12 or 5? None, right? Neither one of them. So delta x in the equation, right? So delta x it should be delta x in here, the equation. So delta x in the equation is the amount of difference between how much you stretch it to the equilibrium location. So that means here, this is delta x. Okay, it's the amount that you actually disturb it from. So if you have a spring that's originally 5 meter and you stretch it to 12 meter, the delta x, which is the change in its length, is actually 7 meters. Of course, you can also compress a spring. So if you compress a spring to, let's say, 2 meters, then in this case, the change in length will be 3 meters. So sometimes the question will just ask you how much is it stretched, how much is it compressed. So you don't have to worry about subtracting from the normal length. But sometimes a question will actually give you the normal length, so you have to worry about it. So let's do 2 quick examples. This section is very, very easy and quick. So a force of 200 Newton stretches spring 30 centimeters. So what is the spring constant of the spring? How far would this spring stretch with a force of 100 Newton applied to it? So now, first of all, we see that 30 centimeters. So the change in your length is, so stretches the spring 30 centimeters. So this 30 centimeters is a change in length, but we have to do it in meters. So 0.3 meters, right? Okay, so now let's use that equation. So we have our, how much force, right? Okay, so how much force? So we have a 200 Newton force. So let's do a force. So this is the force equation, which is negative K. Which is technically, when you use that equation, you don't have to put the negative in there. Okay, the negative is just there to tell you that the force will be opposite to what you did to it. So when you stretch a spring, the spring should provide a force that's countering that stretching. So we have a 200 Newton force, and we're looking for the spring constant when you're stretched by 0.3 of a meter. So use a calculator and we divide 200 by 0.3, we can find out that the spring constant, we'll find out that the spring constant is about 667 Newton per meter. Now, what does that mean? That means for every meter that you stretch a spring longer than its original length, you're going to get 667 Newton of force trying to pull it back. If you stretch it for 2 meters, you're going to have double the force pulling it back. If you stretch it for 4, 5, 6 meters, you're going to have the amount of force that is 4 times, 6 times more than that spring constant. But remember, nothing can actually be stretched forever. There is an upper limit, although we're not talking about that in here. You cannot just take a spring and stretch it for like 1,000 meters, right? It doesn't work. Maybe some spring, a really long one, can stretch that long, but normal spring cannot. So you can only stretch it so much until it fails. But before it fails, we can use that equation. Okay? And at what point does it fail is very dependent on the type of spring. So how far would this spring stretch with a force of 1,000 or 100 Newton? So now we're looking for how far will it stretch, which is delta x. So that means with a 100 Newton force, so the force equals to K. Now we do have K, which is something that we just discovered, 667 Newton per meter. And so what we're actually looking for is the delta x. So, okay, so we use the same spring and then we put a force of 100 Newtons on it. How far will it stretch? So you then can calculate the amount of stretching will be exactly 0.15 meters. I mean, you don't even actually have to do a calculation to know that, because if you look at the previous example, look at the first part, right, part A, 200 Newton is enough to stretch a spring by 30 cm. So 100 Newton, which is half the force, will stretch the spring half as much, which is 15 cm, right? So that's another way to look at it. Now, let's look at another one, a trampoline. So this one, so let's assume that you have a trampoline, which looks something like this. Okay, so trampoline, and you're gonna jump from here. So you're jumping from trampoline has a spring constant of 3,000 something Newton per meter. How far will the trampoline shrink when a 70, okay, so 70, obviously, forgot something, kilogram person, when a 70 kilogram person lands on it from a height of 2 meters? Okay, so there's actually going to be a few more steps. So part A, step 1 is you start jumping. Part B is going to be something like this. So you have this trampoline, which is now we're looking at it from the sideway view, right, of the trampoline. So what happened is when you look at it from the side, okay, so the moment you land on it, okay, so now at this moment, all of the potential energy that you have, remember from earlier, we talked about conservation of energy. So let's say at position A, you have potential energy of a certain amount. Let's say that certain amount is this apple. So once you jump down, okay, so once you're down here, when you're on the surface of the trampoline, now how much kinetic energy are you going to have at that time? So if you remember from previous classes, you remember that, hey, the energy should be conserved. So the amount of potential energy that you start at the top should be equal to the amount of kinetic energy that you have at the bottom. Now, so the kinetic energy that you should have when you just hit the trampoline should be the same as the potential energy that you have when you're at the top, right? So that means if we know the potential energy at the top right here, we'll know the kinetic energy when you hit the trampoline. Now, but when you hit that trampoline, you're going to hit it with a lot of speed, right? So you're going to hit it with a lot of velocity because you just jumped down from like a height of 2 meters. Then what happened? Well, then you have the third part of this, which is the trampoline is going to stretch in the other direction, which is the trampoline is like an elastic piece of fabric, right? So it will stretch it, and so when you jump onto it, what happens? It will stretch until you stop completely. So basically, the third picture is you at this location. Okay, so at that location, what happened? Oh, sorry, this is going to be part C of your jump. So at this location, you will have a speed of 0 because the trampoline has stopped you. So where does all the energy go? So let's say you started off with like 100 or 1,000 joules of potential energy. Then at point B, you have 1,000 joules of kinetic energy and no potential energy because you have jumped. You have reached the level of the trampoline, and then you go even lower by a little bit, and your velocity is 0. So at this point, where does the 1,000 joules of kinetic energy go? Well, remember, energy cannot be created or destroyed. It can only be transformed from one form to another. So therefore, where's the energy? The energy must be stored now in the fabric of the trampoline as elastic energy. So at this point, you'll have elastic potential energy. And how much of that do you have? Well, exactly the same amount of compared to the kinetic energy that you had earlier. And it's also exactly the same amount as the potential energy that you have earlier. Okay, so now knowing that, this calculation, the following calculation is quite easy. So I will say, how much potential energy do we have? Now, this potential energy is mgh. The mass is 70 kilogram. G is gravity. H is the height of 2 meters. So that you can use a calculator Now, I have a calculator in here, so let me actually forgot to calculate that in advance. So let me just calculate it really quickly. So 70 kilogram times gravity, which is 9.8, multiplied by 2, 1372. So 1372 joules of energy. Now that is the amount of energy that goes into here. That's also the amount of kinetic energy that you have when you hit the bottom. That's also the amount of stored potential energy in the fabric. Assuming that the world is perfect though, right? Assuming that there's no friction lost due to heat and everything, assuming there's no vibration. Now we can make that assumption in here as a practice. So assuming the world is perfect, that is also the amount of energy that you're going to have down there. So, okay, so conservation of energy tells us that so therefore we have our spring potential energy, which should equal to the potential energy when you're at the top, which is equal to 1372. Now, so how can we use that? Well, the spring potential energy has the so the spring potential energy has this equation, which is a 1/2 k delta x squared, remember? So what we're looking for is how fast will the spring stretch, which is the delta x. So which is there, here, delta x. Okay, how fast is the spring stretching in the opposite direction? We have k. K is, from the question, 3,430 Newton per meter. So use a little bit of algebra. So what you want to do is look at this equation. So how would algebra help you solve this? So multiply both sides by 2 is the first thing I would do. Divide both sides by 3,430 is the second step. And then that will equal to x squared. So take a square root on both sides. So I'll let you deal with the algebra in here. And I'll just write down the answer. It's about 0. So it's not even going to be a meter. So it's going to be 98 centimeters in one direction. And that's it. Okay. So the worksheet for these questions are right below. I will give you the detail on which question to do and everything on the post that we have on the courseware page, of course. Okay, so this week is very simple. I will also post the assignment. So remember, after each chapter, we have assignment. So obviously at this day and age, we are not going to be able to do a chapter test on this chapter. So for now, just complete the assignment, I guess, to conclude this chapter, and then we will move on to the next chapter after that. So for this week, I'll give you a bit more time because there is an assignment. Okay, so I'll put everything in detail on the blog post. Okay, goodbye everyone. Stay safe.